Hello, everyone. Welcome. Thank you so much for joining us today. Um, we are really excited to have Len here from Exo-Tec. Myself and Elisa are here representing the Acelab team. And before I pass it over to Len, I'm going to do some quick housekeeping items. And first and foremost, I'm going to take you over to Acelab. So in just a moment, you should be able to see my screen. I'm here on Exo-Tech's Acelab page. So here, I mean, if you're not familiar with Acelab, if you're looking to do some kind of materials research, a good place to start is using this search bar at the top of the screen. You can do our AI search, or in this case, if you're looking for a specific manufacturer, just click this button here. And here on Exo-Tech's page, we've got some really great information here for you. We've got Len's contact information as well. So definitely check out their page when you have some time. I'll drop a link in the chat for you. And here we have their product. You can click into this page to get a lot more information on this product. And you can also click right here and save it to your firm library. That way you have it for future reference. But definitely check out their page. Again, we have some great information here for you. A couple things, other things to make note of before we start. This is an AIA-approved presentation. So if you're worried that we didn't already get your AIA number upon registration, we will put a form in the chat for you as well. You can fill that out to ensure that you get credit for today's session. We will also be doing Q&A at the end of the presentation. We'll get to as many questions at the end as we can. If we're not able to get to all of them, we'll send you an email with an answer to your question, but you'll see that little Q&A button at the very bottom of your screen. Click that, drop your questions in there, and again, we'll get to them at the very end. You will also see a webinar poll pop up on your screen during the webinar. It will come up about 3/4 of the way through the presentation. That is an optional poll, so if you're not interested in getting any kind of follow-up from us, you can just click the X, it'll go away. However, if you are interested in getting follow-up information, fill that out with any specific questions you may have or items that you're looking for. We're going to connect you directly with Len and his team after the webinar via an Acelab conversation. So keep an eye on your inbox for that Acelab email connecting you with Len. You can respond directly to the email, or you can log into your Acelab account and respond there. It's a great way to get additional materials or just specific questions answered. Lastly, we will also do a post-webinar survey. So we really appreciate any feedback that you have. Feel free to leave any notes or comments there at the end. And with that being said, Len, I will go ahead and pass it over to you to get us started.
Okay, thanks, Kayla, and thank you for everybody for taking the time to attend. I hope you find this very informative. If you read my bio, you'll see that I was a founding member of the Air Barrier Association of America. I was actually incorporated it. I was vice president the first 2 years, president for 8 years because nobody else would step up. But I finally stepped aside when we got air barriers in the International Energy Conservation Code. And then I watched for 10 years as all these products flooded the market with all these different claims. And we just kind of stumbled along, and there's some disasters, there's some near disasters. And it took about a decade to weed everything out and get back to a handful of really good products. It also had a big effect on masonry veneer anchors, and I put together a presentation for the Boston Building Enclosure Council for the Boston Society of Architects chapter. That really helped too. So what I decided to do when I saw this coming around in my consulting work, when the International Energy Code got rid of continuous Z furring, I started having my architects clients that I consult for showing me things that, what do you think of this attachment system? And I was like, well, it's not bad, but it doesn't do this or it doesn't do that or whatever. And so I I sat down one night and wrote a list of everything you need because I'm a little bit OCD in a cladding attachment system, and then started comparing it to that. So that's what this presentation is based on. So it is AIA approved, an AIA certified presentation to the Air Barrier Association of America. Here's our 4 learning objectives. We're going to teach IBC IACC requirements and send some basic requirements, then beneficial requirements, and then hopefully you're being empowered with the knowledge to select and specify an attachment system that'll fulfill the needs and goals of your project. So here's the list I came up with for your rain screening cladding attachments. Number one, it's got to withstand the loads imposed on it. I'm happy to report that they all do. From the test data that I've read through on all the websites. It has to comply with IBC and IECC requirements. I'm surprised that there's many that don't. I felt that it shouldn't burn due to, the requirements for non-combustible construction. And it has to result in minimal thermal bridging through the continuous insulation. So when I came, to our building enclosure council in Boston, we looked at the different systems and it has to be non-combustible. And so therefore it's got to be metal. So now to to reduce your thermal bridging, you really need to minimize the amount of metal going through that continuous insulation. The least amount of metal to get the job done, the better. I wanted to install really easily with few parts to assemble. I wanted to provide for the required adjustability without having to shim in each and every veneer panel that you have to put up with. I'd rather have the system adjust to one plane and then they can just put the panels right up without having a plumb or range them. I wanted the cost to be reasonable. The costs are, range from like 350 a square foot from my data up to $13 a square foot. So there's a huge cost range there. I didn't want it to require cutting and fitting of the continuous insulation around the cladding attachment system because that requires more labor to do that. I didn't want it to require shop drawings. We didn't need them when we were using continuous Z-furring, and now some systems require you to have them, and then they have to go through the review process. The contractor reviews them, the architect reviews them, they get stamped. That's just one less step in the construction process if you don't need shop drawings. And then what was really important to me was to provide for the mechanical fastening and the continuous insulation within that cladding attachment system. If it doesn't do that, then fasteners have to be put through the continuous insulation. And there's missed studs, there's holes in your air barrier, and that's a big concern to me because I spend so much time in the Air Barrier Association of America. All right, so moving on, let's look at our code requirements. There's IBC, International Building Code requirements, or non-combustibility requirements, and fire ratings for load-bearing members and other components in the exterior wall assembly. So looking at Chapter 6 for Type 602.2, Types 1 and 2 construction are those types of constructions in which the building elements listed in Table 601 are non-combustible materials, and I'll show you the table. Type 3 construction is that type of construction which exterior walls are of non-combustible materials. Type 4 construction, this is your heavy timber construction. I don't know, it's not used too often. I don't know if anybody uses it out there. But again, they have a non-combustibility requirement for exterior wall materials. Type 5 construction is your wood frame, and that can be any type of material permitted by the code, combustible or non-combustible. So Chapter 7, 704.10 states exterior structural members, for exterior structural members, load-bearing structural members within the exterior wall or on the outside of a building structure shall be provided with the highest fire ratings per table 601 and 705.5. So to me, that means your cladding attachment system because it's bearing the gravity load of your cladding, and it's also transferring your compression and suction wind loads back to the structure. So in my opinion, and most of the experts that I know, high-end consultants feel that these are the cladding attachment system is our load-bearing elements. So here's table 601, and it just shows you for the different types of construction, the fire ratings that are required. So bearing walls, exterior walls, which any wall bearing the load of the floors above have to have fire ratings, except for type 2B construction. And for non-bearing exterior walls and petitions, they refer you to table 705.5 for those elements that provide the strength in the wall. And so 705.5, this is your fire separation distance requirements here. So less than 5 feet. You can see all these different types of buildings need to have a 321 hour rated components in that wall that are bearing a load. And as you get further and further away, then the fire ratings drop down to zero. So if you're above 30 feet. So there's a bunch of manufacturers out there that use fiber reinforced polymers or FRPs. In my opinion, they burn. I know, well, actually, I know they burn. And the people, our group at the Building Enclosure Council say that the code is pretty specific, saying you can't use that. Our interpretation of the code, but they were hanging their hat on Chapter 26 or Section 2613, where it says a fiber reinforced polymer the fiber reinforced polymer shall not exceed an aggregate total of 20% of the area specific to the wall which is attached, and single elements should not exceed 10%. And No contiguous sets of architectural elements, being the key word here, shall not exceed 10% of the area of the specific wall. In our opinion, my opinion, and those many others and many architects I talked to, this is intended for decorative elements, like it says, architectural elements like trims and whatnot. It shouldn't apply to an element that's bearing a load in that exterior wall, or an element that's carrying your cladding system on there. A lot of other manufacturers say, "Oh, we passed NFPA 285." This is not a materials test, as many of you know. This is an assembly test. First of all, it's a 30-minute burn, so there's no way you can get a 1, 2, 3 hour fire rating out of that NFPA 285 test. The the failure criteria are flame spread and temperature exceedance. So the flames can't go any more than 10 foot above the window or more than 5 feet on either side of the window opening in the test panel. The exterior face temperatures can't exceed 1,000 degrees, and the stud cavity can't be above 750 F, and in the second story room it can't be uh, above 500 F. So just in summary, you got a 30-minute burn. This test for fire propagations. Failure criteria is flame spread and heat generated. Rain screen cladding panels falling off the test panel does not constitute a failure according to NFPA 285. And if you have a cladding attachment system with elements bearing a load that burn, you can this can happen in real life and in the NFP 285 test also. So again, this is not a fire rating test. So here's a picture of the test. I don't know if anybody's actually got to witness it. I did down at Intertech down in San Antonio, and it is a violent test. We're standing about 50 feet back, and it felt like my face was going to melt. But you can see how they run this test. Here's a 3D view of it. So you have your burn room where you light this bar on fire, the gas bar on fire, and after so many minutes, you roll up this other burn bar that's on a cart on wheels, and you let it burn. And you burn it for 30 minutes. If it hits, the flame spread goes beyond the 5 foot on either side of the window and 10 foot above the window, the test shuts down and fails. If you're any of the sensors, the thermocouples in the wall hit those, the 1,000 degrees on the outside of the wall, 750 inside the studs, 500 in the room above, the test shuts down and you fail. So the other thing that I see many manufacturers point to is ASTM E84 test. They said, "Oh, we passed it." Well, this is not a pass fail. This is a characterization test. At ASTM, I've spent over 20 years on ASTM. We used to call it the tunnel burn. It's known as the Steiner tunnel test. And what it does is evaluates the surface burning characteristics of building materials. It was primarily used, it was written, the intent was to assess the burning characteristics of common interior finished materials like wall coverings, ceiling tiles, flooring, to determine their suitability for use in specific occupancies. And so what it does, you run the test and you get what's called a flame spread index, or FSI, and a smoke developed index, an SDI. These are the two criteria. For the flame spread, the index is the standard is red oak equals 100 degrees. So there's 100, and I'm sorry, not 100 degrees. It's red oak has a flame spread index of 100, cement board is 0 because it doesn't burn. And that's the comparison that each of these products are measured to on it. So a Class A rated or Class A rated for under ASTM E84 is a flame spread index of 0 to 25. Class B is 26 to 75. Class C is 76 to 200. Um, most of the codes out there, NFPA 101 and International Building Code, want to see a Class A flame spread of 0 to 25, and all of them uh, they require a smoke developed index of 450 or less on that. So again, they point to say, oh, we have fire resistance because we pass ASTM E84, we're Class A, and it's not um, a fire resistance test, so to speak, or a fire. It's not a fire rating test. It's a resistance test. It measures how much it burns and how much smoke's developed. So I have a product called GMX. It's just a spray top, no manufacturing company. It's just a spray stop for when you do spray foam insulation. You put it around doors and windows so you can square it up and get the full thickness. And after the air barriers went into the code, and many of them were asphalt based, sheet or fluid applied. And somebody smartly said, "Why are we covering the outside of our buildings with something that burns with this asphalt-based products? What can we do to check it?" And so they took this EE4 test, which was basically for interior interior materials, and they said, let's apply this to air barriers put on the outside of the building, and you had to be Class A. In other words, you could still burn, but not that much. So I got asked for this for my JMX product, and it's PVC, it's window grade PVC, which I knew burned. I knew I wasn't going to pass. So you can put an additive in it, and that's what some of these manufacturers, FRP, will say, well, we have a flame retarding additive. I have it in mind so that I could get the Class A rating. It still burns. This is in my warehouse. It'll still burn, but once you take the flame away, it goes right out. So you can see it burning now. But it's still, in a real building fire, that flame's not going to go out. It's just going to keep burning. So you can see it now. Pull the flame away. It does go out. It is self-extinguishing. So I don't think that's gives you a pass to go ahead and use something that burns as a building, a cladding attachment system. So, all right, on to the IECC, our code requirements that we have wall assembly U values. We have performance requirements, which I prefer, and we're getting more and more toward performance requirements, but there's also prescriptive requirements. And then there's also a definition of continuous insulation. So if you look at your performance requirement table here, I'm in zone 5. I'm up in Massachusetts. So if you look at above grade walls, metal framed above grade walls in zone 5, you need a U factor of 0.055 for your whole exterior wall assembly to meet the intent of the code here. A lot of people don't identify really well with the U factor. They're more used to an R value, and I'll show you how to convert that so it's more understandable. So in my climate zone, the U factor is 0.055. The U factor is the inverse of your R value. So if you divide 1 by the U factor, you're going to get the R value of the whole wall assembly that you need. And that is for my area, R 18.18 to comply with the code. The code also has this prescriptive compliance requirements for metal frame buildings in zone 5, where R10 continuous insulation on the outside of the sheathing, and then R13 within the studs. I don't know if you noticed on the opening slide, I am WFI certified and WFI advanced certified. That's a lot of what I do in my consulting is I evaluate exterior wall assemblies to see if they're going to fail or not. And if you do this in a medium or a building with medium or high interior relative humidity, you're going to hit the failure criteria for WFI for RH values within the wall. So I don't like using this. I like to put all my insulation to the outside of the sheathing and then go by the performance requirements rather than to go to prescriptive requirements. So the IECC also gives you a definition of continuous insulation, which is insulation material that is continuous across all structural members without thermal bridges other than fasteners and service openings. Um, so why did they do this? Because thermal bridging is a big issue now. We're getting smarter with our insulation instead of just in the past, we want just more, more, and more. Now let's make our insulation as effective as possible. One way to do that is to get rid of your thermal bridging. Another way we dealt with the air barriers. You don't want air flowing through and around your insulation. And that helped with it too. So it needs to be, the thermal bridging needs to be dealt with in order to comply with the prescriptive requirements of the IACC. So what we used to do is continuous Z-furring. Now we can't do that anymore with that definition. The reason being is if you look at an analysis on this, and this is one that I did using Therm from Lawrence Berkeley Laboratories. Um, this is something, it's a free download that you can use. You build a wall. It's kind of clunky to use. It's hard to use. It was originally called Windows and it was adapted for wall assemblies. In Windows, you had aluminum glass and some spacer material. A wall assembly, you have a whole bunch of material. So you really have to do a lot of digging to plug in all the conductance values you need to do it. There's a better program out there called Flixo, Flixo. It's developed over in Germany to be used with passive house where that you can do this 2D thermal analysis. But in using the Therm program on this, what I found is that continuous Z furring at 2 foot on center reduces your R value by 46% of that continuous insulation. So if you have R10 continuous insulation on the sheathing with the Z furring, you're only at R 5.4, and therefore you're not going to comply with that code. Or if you put all your insulation out there and put the Z furring in, you won't get to where you need to be to comply with that code. The code in 2018, I was happy to see them finally start penalizing for thermal bridging within their steel stud. So they have this table in there. So if you have a 6-inch stud with 16 inches of insulation and R19 batts insulation in that stud cavity, your R value you can use is only R 7.03. So if you do R 13, you know, like it says in the prescriptive requirements, R10 continuous with continuous Z furring, you're at R4 5.4 plus your effective value of 3.5 inch R13 cavity insulation 5.98. You're not anywhere near that R8 R18.18 that you have to do that's required on a performance basis. So as I mentioned before, the fasteners for the continuous insulation are also a big concern for me because there's a lot of thermal bridges. It creates a lot of thermal bridgings in Massachusetts in our stretch energy code and what's coming in the 2024 International Energy Code. You have to account for all your thermal bridging through your continuous insulation. In Massachusetts, all the top consultants and experts that I've talked to says, yes, you have to factor in the thermal bridging for your insulation fasteners in your derating calculation for your insulation. And the big thing to me is that these fasteners can result in thousands of unsealed penetrations through the air, water, and if it's a vapor barrier also. And this is what I see a lot on jobs in my consulting when you use these insulation fasteners. That orange is your air, water, and vapor barrier. That's a hole. Now, there is no testing for that. I pushed the Air Barrier Association of America for years to get something done. They finally started something when we had enough money to do it. We started a research project um, on this, and COVID shut it down. And so we were working in conjunction with Oak Ridge National Laboratories in Oak Ridge, Tennessee, and Tremco volunteered their lab for us to start doing all this research and testing, and the people at Oak Ridge couldn't travel during COVID, and now the person in charge of it can't travel at all due to health reasons. So it's kind of sitting there, and I'm still trying to kick them in the butt to try to get something done on this here because that's a concern. It's a hole in your air barrier, it's a hole in your water barrier, and trying to find the studs through all this insulation is an issue to me also. So this is why I feel if you can have a cladding attachment system that mechanically fastens your continuous insulation, you're going to be much better off. All right, so looking at the 2024 International Energy Code, and like I said, in Massachusetts, we have our stretch energy code that requires this already. It requires the derating of the insulation based on the amounts and types of thermal bridges through your continuous insulation layer. This is accomplished by factoring linear thermal bridges and point thermal bridges. If anybody's worked on a passive house project, passive house, this is required under passive house. They do this to get the true R value of your insulation in the wall. They factor in all these thermal bridges. So um, in C4 402.7, they mentioned thermal bridges and above grade walls. They have to comply with this section. There are some exceptions. Buildings located in climate zero through 3. If your thermal bridge is less than 3 BTU per hour per square foot per degree, there's a coping flashing exemption. Then thermal bridges accounted for in the U factor, C factor for building thermal envelope. This is what Passive House will do also on this. So the cladding specifically mentions cladding supports, and I don't know who wrote this, but I know I have some issues with it, and I know some people from some of the big name consulting companies are working with the Code Council, the International Code Council, to get this cleaned up. But for cladding supports, all it says is linear elements supporting opaque cladding systems shall be offset from the structure with attachments to allow the continuous insulation where present to pass behind the cladding support element, except at the point of attachment. There are a couple of exceptions to that for that, like I said, is in for passive house, they'll do this here, and you can meet that exception if you're going with passive house or anchoring for curtain walls there. So basically, it tells you to derate for linear thermal bridges and point thermal bridges. And in my opinion, and many other experts in the industry, this includes your insulation fasteners. And I've spoken to people in passive house that work passive house experts, and they said, yeah, your fasteners are factored in for your thermal bridging, for your derating. So under the International Energy Code, your linear thermal bridges are assigned what's called a PSI value, PSI, and that's the symbol for it is this trident, this italic trident, and your point thermal bridges are assigned a chi value, and that's a subscript italic X. You'll see that used for it. So um, here's the rating equation that's in the code that you have to use. And I know that whenever you see a math equation that doesn't have any numbers in it, eyes glaze over. But I'll try to explain this to you. It's actually not that complicated. So to get your U derated for your U factor, and they do switch back and forth between R derating R value and U derated, it gets a little complicated, but I'll try to clean that up for you. So basically, this is epsilon. This means the sum of all your psi values times the length. So each different linear thermal bridge has its own psi value. You times that by the length, and then you sum up all those. And then you add to that the sum of all your point thermal breaks or chi values times the number of point thermal breaks. You divide that by the total area of opaque wall and take that number and add it to your U of your opaque insulation, and you get your U derated. So I hope that was pretty simple. I'll break it down a little bit more. Your linear thermal bridge derating, your U derated takes your psi value times the length divided by the total area of opaque wall, and add that to your U value of your opaque wall, and you get your derated U value. So if you want to look at the point thermal bridges, which are your chi values, you take that times the number, again, divided by the total area wall, plus your U derate, U opaque, and you come up with the actual derated value of your insulation. So in the 2024 code, IECC, they only give you psi factors. I don't know why they don't give chi factors for your cladding attachment system. Um, it gives you a psi factor of 0.2 if you're compliant with that you have to use, but if you're compliant with 402.7 when you're doing your calculations, and non-compliant is 0.3. These don't work at all. There's people working on it to try to explain this. I don't know how this got into the code, but if you use these values and you take 3 inches of mineral wool, which is our 12.9, and you take the 0.2 times 10,000 linear feet. So if you have a 20,000 square foot building, every 2 feet times the perimeter, you get about 10,000 linear feet. Divide that by your 20,000 square feet of opaque wall, you get zero point 0.1 plus, the U factor of your R 12.9, your 3-inch mineral wool. You end up with R5, you go from R 12.9 to R 5.63. So your D rating is 43.6% or 0.436. If you use this calculation, you try to get up to the R value you need for your assembly. It's really hard to get there. And it's even worse if you go with non-compliant. This just doesn't work. I will tell you there are people working on this right now to try to get this cleaned up in future codes, additions to the code. So the best way to do this is get 3D model Psi and Chi values to calculate the derating factors for your cladding attachment systems. There are some manufacturers that have these done, but I think more need to do it. A lot of them will just show a table or a number, but you really need to get these values. They can be done, and it's not that expensive to do it. All right, so let's take a look at the systems that are out there. So we have these FRP Z-girts. There's many manufacturers of these. There's more coming every week. They say, oh, we're true thermal break, but they still have an R value, which is a resistance to the flow of heat. It's really low. It's zero point 0.7 for the fiberglass base. If you go carbon fiber is your fiber reinforcing, it goes up to R1, so that's a little bit better. But it's still, you do have a lower R value at these locations when you do it. So there's few parts of these. They're easy to install. You get a seal at the fasteners at the backup wall where you have the fastener go through your air and water barrier. You can see the studs. You probably, hopefully, don't miss any. There's no shop drawings needed. The cost is fairly low. The problem is that FRP burns. So I don't think you can use it in non-combustible constructions. Some manufacturers, the insulation fastening is friction fit. Others they can retain the insulation there. There's no adjustability in this, and you don't want to be shimming back here because you don't want convecting currents going behind your insulation. So you have to shim out along the front where you attach the panels. I think the max spacing I've seen is 2 foot, and there's some manufacturers and some studies out there that don't like seeing your screws going through this leg of the FRP. Of course, that versus metal, the FRP is going to have a much lower pullout. There's a reference to the American Society of Civil Engineers that said when you drive a screw through this, it 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 damages the matrix of it, and in their opinion, you're going to get a failure some point down the road. I don't know where, and nobody's considered that. So, um, another company that makes this actually, so I'm sorry. So I did an AI search for FRP burn temperatures here. So it said the polyester and vinyl ester resonance, they're going to burn from 662 to 932 degrees. Your average building fire, and you can look this up, is 1200 to 1800 degrees, and it depends on the fuel source and how much is in there. If you go to epoxy resins, the burn temperature is 752 to 1022 degrees on there. These values are well below a building fire, and the building fire is going to burn for more than a 30-minute NFPA 285 test. So that also says in practical behavior, FRPs don't typically burn like wood, but undergo decomposition. They call it pyrolysis, where the resin breaks down first, and the glass fibers are going to last, or carbon fibers are going to last longer. And this typically starts between 572 and 752 degrees F. So then I look for what's the extrusion temperatures, because if you're going to extrude these, a lot of them said they're pultruded, which is, they use a vacuum pull on one end and they push on the other end to get it through the die to shape it. Obviously, they have to be below your burn temperatures. Otherwise, your product's going to burn up. So this is what I call the melt temperature. So, you're looking at 200 or 250. Um, um, up to about 392 degrees is where they'll these run these extrusions at. They don't want to get into the burn temperatures because they don't want this to burn. So these will actually melt before they burn on a building during a fire. And this is why myself and a lot of experts don't want to see these types of products used. There's another FRP product out there that actually deals with the screw pullout in the FRP by placing pieces of metal in there. That gives you better pullout. For these types of products, low thermal bridging, few parts, easy to install. You get the seal at the fasteners at the backup wall. You don't need shop drawings, and it is low cost. For cons, excuse me, it does burn. I and many experts don't think you can use it on types 1 through 4 construction. This one, the insulation's friction fit. They have a little ridge here. I don't like that because it holds water, a little bit more water than the other ones. When I have an architect that hires me consultant in on our wood frame construction, we're doing a lot of pedestal construction out here. And they said, well, I can use it because it's type 5 construction. I go, can you do me a favor and just turn these vertical? I want the water to run down and out of the wall. I don't want any stops to the water. I don't like trapping water in walls, especially in the Boston area where it can get below freezing and you can have that water freeze inside the walls. There's no adjustability in this system. Excuse me. And again, I think the max spacing I found on their website was 2 foot. So I've seen some of these metal systems out there. I haven't seen them used too often. We had one company that came in to show us one of these at the Building Enclosure Council in Boston, and we had some issues with it. I mean, they were told, well, the compression wind load is now being borne by this insulation, which does burn. Um, my issue was how they find the studs, make sure they hit them, and then what about the seal at the fastener through there? But for the pros, there's few parts, medium cost, low thermal bridging, mechanically fastens, rigid insulation. I was surprised I was at a convention where somebody showed me this applied over top of fibrous insulation for mineral wool insulation. And I was kind of surprised at that, but there's no shop drawings. Again, your insulation burns, so I don't think this could be used in combustible construction. There's no adjustability. You're shimming all your panels. Seal to fasteners, miss stud rate. And the other thing I don't like about this system is their corrosion protection coating, and I'll get into that a little bit later. This is a heavier duty model of that same one. The same concerns, few parts, medium cost, low thermal bridging. It's just the screws, but there's quite a bit of 1/4 inch screws through here. And it does mechanically fasten your original insulation. Shop drawings are not required. Again, because it's one of the bearing elements is combustible. I don't think that you can be used in types 1 through 4 construction. There's very little adjustability in this. You're shimming your panels. Again, seal at the fasteners, these fasteners here, where you're trying to find the studs, and then what happens when you miss a stud. And this is the same corrosion protection, the ZAM 40 that they have on here, but they paint this black, so you can use it for an open rain screen joint system. So now we have these other fiberglass um, clips here that this system is mounted on. Fiberglass burns again, but again, few parts, low thermal bridging. The spacing here, the maximum spacing I think is 32 inches on center. Typical is 24 for the wind load, sometimes 16 on real high wind loads. But you have 2 1/4 inch screws going through here at 2 foot on center here, which is still, that's like a 1/2 inch of metal going through every 2 foot by 1 foot 4. Um, so a few parts, low thermal bridging, no shop drawings are needed. Cost is fairly low. It burns, in my opinion, and that of many others. You can't use it on types 1 through 4 construction. Doesn't provide for the fastening, mechanical fastening of the insulation. You can see all these insulation fasteners. They add to the thermal bridging. You have to cut and fit, if you can see in this picture, you have to cut and fit your insulation around the system here. That requires more labor. There's no adjustability in this. system here. So you're shimming each individual panel. And then again, the seal at the fasteners here. The back of these are hollow. I have a friend that worked for a big consulting firm, and they said they tested these in their lab at ASTM 330, doing an ASTM E331 test, and they weren't pleased with the results at all. So this is probably one of your more another, there's a couple here most more well-used systems. So this one, it's just a stanchion and a metal rail. Is low thermal bridging here because you don't have a lot of metal going through the wall, but there's a fair amount there. Um, the cons are there's a lot of parts to this. There's some adjustability, but not a lot. It doesn't mechanically fasten the continuous insulation. They say that this rail will, but if you move the rail out a little bit and it's not tight against your continuous insulation, it can fall away from the wall and you get convecting air currents behind it. Now your insulation's not doing its job. You have to cut and fit the insulation around these base plates. It's somewhat costly. Um, the seal at the fasteners here also. I know one uh, consulting firm that makes them embed this red piece in a full bed of sealant when they install those because they're worried about water getting behind it because there's hollow spaces behind these red things too. It does require shop drawings, and then this one I don't like the corrosion protection on this one either, which I said I'll get into a little bit later. You have metal clips and rails. I've seen there's aluminum ones out there, and then there's hot dip galvanized ones. If they are, I'd like them to be G90 galvanized, which many of the companies are that offer them. So aluminum is very corrosion resistant. G90 is pretty good. But these systems are costly, especially the aluminum. The aluminum has very high thermal conductance, and in these systems, you have to account for both your Psi values because you have point thermal bridges and then linear thermal bridges halfway through the insulation. It's kind of a tough calculation to do. For the G90 galvanized, they have it a sheet and then they punch it and bend it. I have a little concern about the unprotected edges there. If it's thick enough, like 18 gauge, probably not as much. And these do require shop drawings. There's more and more of these coming out every month, every year, where they use a stainless steel clip and rail, which is great for corrosion resistance, going to last a long time. Thermal conductance is very low. There is some adjustability. There's more and more systems coming out with more adjustability to these. But as you know, stainless steel, they're pretty costly, and it doesn't mechanically fasten the insulation. You can grab one edge of it, but maybe not the other. I'd like to see that change some way somehow if they can come up with a system there. And here they actually show a gap here behind the red spacer there. This is supposed to be their thermal isolator that a lot of the systems have, so you don't have metal touching gypsum board. But when I look at this, I say, why do you even need that? Because there's a really good thermal bridge in your gypsum sheathing. So a thermal break in your gypsum sheathing. So, um, and this does require shop drawing. So, this one, looking at this one, is low thermal bridging because of its thermoclip. There's a good amount of adjustability in this, but it's probably one of the more costly systems out there. There's a lot of parts. In this thermoclip, if you can see, it is called polyamide thermal break. Um, that burns. So I don't think it can be used in types 1 through 4 construction. That doesn't provide for the mechanical fastening of the insulation as if this is adjusted all the way in, compressed against the insulation, yes, but as we know, walls are never plumb. So if you start adjusting it out, the insulation can fall away from the wall, get convecting currents behind there. And once that happens, then your insulation's not doing its job. It's only modeled with mineral wool on the website, which is a little perplexing to me. And this one does require shop drawings. But back to this polyamide. Polyamide is also known as nylon. So I know if you look at your temperature settings on your clothing iron, the lowest one is nylon. So there's different types of nylon. The extrusion temperature is 482 to 572 degrees on these. So, you're building fire 1200 to 1800 degrees. It's going to be above the melt temperature of this. The flashpoint temperature where ignition temperature is 788 degrees to 842 degrees. Decomposition temperature where it starts to fall apart is 662 to 752 degrees F. And then what they call auto ignition is at 930 degrees. And these are all below the 1200 to 1800 degrees. So I think this is why myself and a lot of other experts don't like using those. Now they've come up with slotted Z's. We can't, everybody agreed to the code. You can't use a continuous Z. And now this company's coming up with a slotted Z. This particular product's from a company that had an FRP, offers FRP products, and I think they're starting to realize that I better get something non-combustible, or it's going to seriously limit my market share. Medium cost, non-combustible. There is no adjustability. Doesn't provide for the mechanically fastening of the insulation. Creates thermal bridge. I don't think that either of these comply with the IEC definition of continuous insulation. So. All right, so back to my 10 points here. If anybody can think of something I should add to that, I will definitely, take the advice of your advice and add to this list. Here's my recommendations. I don't want to specify cladding attachment systems with any combustible bearing elements in any types of construction. I know this will probably upset some people, but I know that when wood buildings burn, they collapse within themselves. But while they're burning, if you have cladding panels falling off the building on the firefighters, I think that's just a dangerous situation and should be avoided. But the code will allow it in type 5 construction. I think you should specify cladding attachment systems that mechanically fasten the insulation to avoid all those unsealed fastener penetrations through the air, water, and vapor barrier. Look for use systems that have 3D thermal modeling to give you chi and psi values or combinations of those. If you demand that, we're going to change the industry where everybody's got it, and that's going to help you out in complying with the 2024 IECC as your state adopts it. When you specify them, go with low chi and psi values and pick, if you have to do a minimum of three, get them similar values, because if you specify three products and one's got a derating factor of 0.9 and the other's 0.75, and they pick 0.75 and you recalc, your derating, and you're like, darn, now I have to add insulation, an inch of insulation to the wall, and the design's already done and you can't really do it. So when you're looking at them, get the chi and psi values and get them close to each other. Um, and again, specify products that have these values so you can calculate the D rating. So this is the end of the technical presentation. I hope it was some value to that. The first question I usually get when I finish the technical part is, so what do we use? Well, I didn't like any of them out there. So what do you do when you don't like any of them? You invent your own. So I came up with the standoff MPV bracket. Very low thermal bridging. I had it engineered that can be spaced 1 foot 4 by 4 foot. So I have 3/8 diameter piece of metal going through your continuous insulation every 5.32 square foot. I built in an inch of adjustability. It's metal, so it doesn't burn. There's few parts, easy to install. It's very cost effective. The feedback I'm getting is we're the most cost effective system on the market right now. You got to seal it to fasteners, fastening it to the wall because we have a flat plate. I'll show you in there. It does mechanically fasten the rigid insulation, the continuous insulation. You can see this black disc there. That is your mechanical insulation fastening. So it doesn't require cutting and fitting the insulation. Like I said, at its space 1 foot 4 by 4, so you can fit a full sheet of insulation between the brackets. Cons, we've sold over 100,000 of them and we have had no complaints and no failures. So here's the bracket. So we have the base plate and then our standoff, which is the round part here. And this is the thickness of your insulation. Here's your insulation retainer that's going to crank down on top of that. We have our top plate, which threads in and out. There's an inch of adjustment built into this, our in and out and adjustment. So you can adjust them all to the same plane and then put your attachment rail on there, which 99 times out of 100, well, has been hat furring. So this is just the different components. And you see these threaded studs here. They're called PEM studs. This actually saved the invention because if I had to weld those into place and get them perfect, it would have cost $32 a bracket for me. But now we have it a lot less than that. And this is what a PEM stud is. It's basically a rivet, and they slam it in with a PEM serter. In all reality, I didn't think it was going to work. I think when you put a compression load on, it's going to pop off, but it ended up working. So I had an engineer calc it all out and said, show me what I need. And, he said you need 32-pound gravity load for compression and suction wind load. You need 266 pounds force there. So we prototyped it with those PEM studs, brought it to a testing lab. They put it in their Instron machine. They bent it. They pushed on it. They pulled on it. And none of them tested to failure. But what happens when that curve starts to bend, there is what the failure point is because it's starting to bend, but none of them completely failed. So they came up with these values: 60 pounds for bending or gravity load, 550 for compression and tension. So calculated versus tested, we came in almost double, which we're really happy with. What does this mean? The bending load is it fails at 11.25 pounds per square foot of veneer weight. So we say don't go over 10. If you do, just tighten up the spacing. We've had to on other jobs when we had a one with a quarter-inch core 10 steel veneer where we had to go 16 inches by 16 inches to take the weight of the veneer because that was 24 pounds a square foot. Compression and tension load, that's almost a 300-mile-an-hour wind load. We're never going to see that. The highest wind speed ever recorded was a hurricane in Texas in the 1960s was 188 miles an hour. So here's your typical layout: 1 foot 4 by 4 foot for the base plates, screwing the top plates, fasten down the insulation retainers, then take a simple hat furring. I said, let's just supply the bracket hat furring. We don't want to be shipping this all over the country. You can buy it at any wallboard supply place, and there's usually more than a few in every metropolitan area where you can buy these. They stock it in 7/8 inch thick, G90 galvanized. So why bother? And then they can buy the screws locally too. So we just sell the bracket, and this can be picked up anywhere, which helps keep the cost of our system down. We have some contractors that like this attachment rail for their filler strip at 2 foot on center. And I said, well, if you want that, why don't you just put some flat stock instead of adding another row of hat furring or attachment rail like some of the other systems have. For the tall panels, we can go 1 foot 4 by 4 foot, run the attachment rails, the hat furring horizontally, and attach our panels to that. If the contractor, I've one a couple of Massachusetts are kind of adamant about, I want this at 2 foot on center because this is what we're used to, our guys in the field. So not only can we attach the panel, we can do the filler strip also on that. I said, if that's the case, you can open up your spacing horizontally to 32 inches and you're still getting that one bracket, 1/3 diameter or 5/8 or 3/8 diameter piece of steel going through the wall at every 5.32 square feet. For the thin, what they call the single ply metal siding there, the kind of siding you can hold in your hand and flip your hand back and forth and it'll flop. You can't go more than 16 inches on center for that, for the spacing, for the attachment. So you can go 4 foot on center. And then my rep out in the Denver area said, hey, what about thin brick? Can we do thin brick? I'm like, sure, why not? So we can do that same system and then put your tray system, your thin brick tray system, attach it to that and put your brick in. We just finished a job in Massachusetts here where, there's the brackets, here's our attachment rail. I would love them to go on vertical, but they said, no, horizontals, it's so much easier. And so they ended up doing that. Here's the trays, the brick trays. Here they are, the bricker and the guys pointing it up, and then here's the finished product. I think there was like 13 of these windows here where they put it in. The rest of the brick was conventional laid in place. I did do 3D thermal imaging. I hired RDH to do that. Here's a copy of the report, and they ran through it, and they gave me this table in there for our results of, depending on that assembly, here's your 2-inch mineral wool, XPS, polyiso, 3-inch, 4 inches, cold roll steel, stainless, and you can see stainless has a lot less conductance than cold roll. And they gave me the R values, and I was like, that's great. And then when the code came out in Massachusetts and I saw how to derate, I called them back. I said, hey, wait a minute, I need chi values for my product. And they said, oh, they're in the appendix. So, here's my chi values here. And I'm going to do just a quick showing with 3 inches of mineral. That's the most popular one. Do a quick calculation for you. So the chi value is 0.0409. So if you use that crazy equation that I showed you there, just break it down for chi value, the chi value times the number of point thermal bridges divided by the opaque wall area added to the U factor. So we look at a 20,000 square foot of opaque wall, 3 inches of mineral wool at R12.9, your U factor is 0.0775. To get your UD rated, you take that 0.0409 chi value that I showed you on that report, and you divide 20,000 by 5.32, add back another 10%. So you have 4,135 brackets or point thermal bridges times the chi value divided by the 20,000 square feet of opaque wall plus the 0.0775, you bump your U factor up to 0.0839, or you drop your R value to 11.91. And if you do the math between the difference between derated and opaque, you get an 8.25% increase in your U factor. If you want to switch that over to R value there, you take your R 12.9 minus 11.9, the 11.91 we came up with. There's your difference divided by the 12.9. It's 0.076 or 7.6 decrease in the R value. So your R value derating factor is 0.924. So you take 92.4% of the R value of your insulation. So you can see there's a very minor effect here. And from what I gathered on the websites of the manufacturers that make the FRPZ fairing, their derating factor is about 0.95. So we're pretty darn close to that because they have a lot more linear foot of their rail, and I just have these points, a lot less point thermal bridges. So as far as NFPA 285, I'm friends with the guy who wrote it. His name's Jess Beidel. He's retired now. He worked for Hughes Associates. And I used to run the ABA conference and trade show every year. I was the chairman of the conference committee. So I got to meet Jess. I had him present a couple times, and I asked him, "What do I do with my bracket?" I showed him my bracket. He goes, "You don't have to worry about that." And so for the low price of $5,000, he wrote me this letter saying it will have no effect on it. Again, here's just your typical attachment using a hat furring. I have had people use a mini Z. I don't know why. They've had to close up the spacing to 1 foot 4 by 2 foot because you only have one leg here and an eccentric load on this leg here. I have one job, we used flat stock. It was pretty heavy gauged. They needed it because it was like a zero lot line. They were trying to squeeze every inch of floor space out of it. So I have standard sizes, but I'll make that stand off any size you want. I'm picking up tomorrow. It's 5.5 inches of insulation. So I'm chasing a job that has 9 inches of insulation. So I can make that any size you need to. The finishes, I went with zinc and yellow chromate plating and stainless steel. There's not a lot of stainless steel available, just the clip and rail. But mine, I do offer it. Why did I go with zinc and yellow chromate plating? We couldn't hot dip it. I know the standard in the industry for in a wet environment is hot dip galvanized, but if I did, then the parts wouldn't screw together. I looked at ceramic, it made coatings, it made it more expensive, stainless. So zinc and yellow chromate offered the closest performance to hot dip galvanizing. And the corrosion resistance depends on the concentration of zinc and the thickness of the coating. So hot dip's 0.98, zinc rich. According to ASTM A153, you have to have 1.5 ounces of zinc coating per square foot of exposed metal, which is 2.2 mils or 1.1 mils per side. So the zinc and yellow chromate is 0.98 zinc content, but I'm only at 0.98 mils thick. Um, uh, per side. G90 galvanizing is 98% zinc content, but it's only 0.81 mils. And the ZM40, which I don't like, is 91% zinc plus 0.36 mils per side. And this is when I talked to the people. The ZAM was developed by Nippon Steel and then brought over to this country, I think in 2016. They take out some zinc and add some aluminum to it. And supposedly in their claim, it lasts longer than the hot tip galvanizing. I spoke to the American Galvanizers Association and we have no comment on that. What we will tell you, it's always the zinc content and the thickness. And they actually, they have in their they have a guide to this now where they show you for G90 it's 0.81, G60 0.54, G40 0.34, and they judge their coatings based on what they call is time to first maintenance, which is defined as 5% rust on the surface of the steel. So at 98% zinc content, 1 mil thick, on an urban suburban environment, you get be 25 years to the time to first maintenance, another 5% surface rust. And that's not going to cause it to fail. But I also looked at, I said, this looks pretty linear. So if you see it 2 inches, it's just under 50 years. And they said, yeah, it's very linear. So I said, so in 50 years, you got 10% um, surface rust. And they said, yeah, pretty much. So I was pretty confident with that. Having that. And then using that table, I calculated it out. So hot dip galvanizing at 1.1 mils times the 25 years is 27 and a half years. The zinc and yellow chromate at 0.98 mils, 24 and a half years the time to first maintenance. I was really happy with that. That's pretty close to hot dip galvanizing. Your G90 is about 20 years. G40 is at 36 mils is 9 years, and the ZAM 40 because they reduce the amount of zinc to from 98% to 91%. It's 8.36 years. So that's why I chose the zinc and yellow chromate. And the other thing I don't like about that ZAM type 40 type coating or the
Len,
yeah.
sorry to interrupt. We are actually out of time. I want to be respectful of everyone's
Oh,
schedules.
sorry.
Are we almost done or
Yeah. Yep. That's about it. But
okay?
they just told me, oh yeah, when you cut it, what happens when you cut it? They said, oh, it'll drag it across and it'll migrate down and protect it. And I was a consultant on a job. That's rust. That's a cut edge there. That's rust there. So packaging, here's just some examples of it now. This is a spray foam job we use it on. There, framed it with the hat furring, put the siding on. This is the job all done. Here's the job they use the Mini Z tall panels here, and you can see the application here. Um, there's another job as a addition to a sports center. They used it on the consultant, didn't like fluid applied, so he made him put blowout patches over every one of them. But here we had the mineral wool. We want 1 foot 4x4, put the panels up. Uh, these panels ran horizontal in this school, so they use that orientation. There's another school with the tall panels where we used it on. Here's ACM panel job. Here's another ACM panel job we just finished last fall at NREL, National Renewable Energy Laboratory. And they want 2 foot by 2 foot 8. Their studs are spaced at 2 foot. And this was the Core 10 steel job. It weighed 24 pounds a square foot that we used it on. So that's about it. Sorry for running over on time. Thank you for attending. Do you want to have time for questions, Kayla, or do you want to just have them submit to me?
Yeah, there was only a couple, so I think we'll just have you follow up via email. So yeah, thank you so much for that, Len. Would you like to wrap us up with any final comments?
No, that's it. Thanks so much for attending. I saw the attendance numbers were pretty good.
Yeah,
Appreciate it.
awesome. And we will be in touch with the folks who filled out the poll. Keep an eye on your inbox for an email connecting you directly with Len to get any further questions answered. And yeah, thank you so much, Len. This was a really great presentation, and thank you everyone who joined today. We hope you all have a great rest of your day.
All right. Thanks. Bye.
Yep.